As you saw in the simulator, a short circuit is a path of little to no resistance. It may be a misleading name. The short circuit is not always the shortest path there is. It's not short in length, it's short on resistance. It's a shortcut from one terminal of the battery to another. We're going to continue to use the industry standard notation that red is high voltage, black is ground or low voltage. If you're lucky, your circuit or your battery is grounded and you've got both. But the current is trying to get from high voltage to low voltage. If your wires are insulated and set up correctly, the current should go in one side of the light bulb, through the light bulb. See the resistor there? It's even zigging and zagging like it's going to be in circuit notation. Out through the other end of the wire, through the black wire, and back into the battery. However, if you are careless or if you keep a messy lab bench, if the insulation on these wires has worn off and you don't notice, if this wire touches that wire and makes an electrical connection, there's a shortcut from the high voltage end all the way to the low voltage end. The original circuit had a resistor in it. It had the light bulb with its tungsten filament in it. That's what a light bulb is. It's a very thin wire filament in a glass that glows white hot. LEDs work by chemistry. They're much more energy efficient, which is why in the 21st century we should be doing everything with LEDs and not old-fashioned incandescent bulbs or CFLs, compact fluorescent lights, which work through a different kind of chemistry and have nasty mercury vapor, so you have to evacuate the place for 15 minutes after you've broken one. But one way or another, they have a significant resistance. If you accidentally drop a wire from your messy lab bench and that wire falls from here to here, or worse, you're sitting around with your giant mug of coffee or your water bottle and you accidentally spill over a circuit board, splash, 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 and a drop or a puddle of water lands from here to here, there's now a shortcut from the battery through the wires and the switches, which are just wires, and the fuse, which is going to be the solution to this problem, albeit a very nuclear option sort of solution. You will have nothing but wire from here to here. That is a path of incredibly low resistance. Now, check your Ohm's law. Same voltage, denominator drops to practically zero. What's going to happen to the current in the circuit if the denominator, if the resistance drops to practically zero? Press pause, do the math in the head, press play to check your work. What's going to happen? You're going to get a ridiculously high current. That's what's going to happen. Your circuit has practically no resistance. It's almost infinitely easy for the current to flow. In fact, the current that's flowing is so high, it's going to be in danger of melting this plastic insulation, causing even more short circuits as the wires aren't insulated and they touch each other when they're not supposed to. And that, in addition to causing the nasty cancer-causing fumes of acrid melted plastic and smoke, you're going to be in danger of causing an electrical fire, which is why a search for short circuit yields very few correct diagrams of a short circuit and treats the word wrongly as a synonym for an electrical fire. A short circuit is a very specific error. It is not engineering code for this done gone don't work. A short circuit is a path of little to no resistance. It's a connection made where no connection was meant to be made. The problem with a short circuit is twofold. If you're trying to light the light and you have a path of little to no resistance and a path of 100 ohms of resistance, which path is the current going to choose? Come on. If you had two lunch lines on Tuesday and one of them was practically every kid in the school trying to get the chicken tendies before they're all gone, and hey, it's spicy fries day, there's 100 people in that line. Alternatively, your dad works in the kitchen and he has a special plate all ready for you with chicken tenders and spicy fries and some of the peas off the top that aren't split with oil with a chocolate chip cookie. No resistance. You just go to the kitchen door and knock, and there is your food. I ask you, which line would you wait in? Would you go through 100 ohms of resistance with 100 people in the line? Or would you go to the kitchen door and trouble yourself only to knock? Show of hands. Come on. Come on. Who's taking the path of little to no resistance? That's right. Everybody does. That means there's not enough current for the light to flow. I think no current is a little bit of an exaggeration, but practically no current. No current to speak of. Negligible current. So of course the light is off. You've shorted it out. Great. And then over here you've got this ridiculously high current that's running so hot that you're in danger of melting the rest of the insulation off the wires, giving yourself cancer from the fumes, and setting the house on fire.